the name of Almighty God, I am Master Sankoshi, and today I want to describe the difficult phrase here in this literature, extra dimensions, which led to the foundation and inception of string theory, provide an elegant approach to force unification. So I want to describe a little about the force unification. The concept of force unification in physics refers to the idea that the four fundamental forces electromagnetism, weak interaction, strong interaction, and gravity may be manifestations of the single unified force at high energies. Electromagnetic and weak interactions have been unified in a single electro-weak interaction at high energies as predicted by the electro-weak theory. The Grand Unified Theory or GUT posits that at even higher energies, the strong and electro-weak interactions may unify into a single electronuclear interaction. Theories suggest that these unifications occurred in the early universe before the separation of these forces. Their search for a unified force continues, with theories exploring the possibility of including the gravity and the unification process. This ongoing research aims to provide a comprehensive theory that explains the fundamental forces of nature. So the rest of the article. With bulk curvature as high as the Planck scale, higher curvature term, namely FR gravity, seems to be a natural addendum in the bulk action. And now I want to talk about the Planck scale. The Planck scale represents the fundamental limits of space-time energy where quantum gravity dominates and classical physics break down. Definition of fundamental units. The Planck scale is defined using three fundamental constants: the speed of light as c, the gravitational constant as a g, and the radius Planck constant as h. Quantum of angular momentum. Planck length is I. LP approximately is about 1.6 multiplied by 10 to the power 35 meters, representing this minus 35 meters, representing the smallest meaningful length scale. Planck time, which is a TP, is about 5.4 multiplied by 10 to the power of minus 44 seconds, the time it takes light to travel one Planck length. The Planck mass, MP, roughly is 2.2 multiplied by 10 to the power of minus 8 kilogram, or 1.2 multiplied by 10 to the power of minus 10 to the power of 19 giga electron volt, divided by c to the power of 2, far larger than a proton mass. Planck energy, the energy equivalent of the Planck mass, around 10 to the power of 19 giga electron volts, divided by c to the power of 2. These units form a natural system where the constants c, g, and h are normalized to 1, providing a scale at which quantum mechanics and general relativity intersects. Physical significance. At the physical at Planck scale, classical concepts of space and time cease to apply. Quantum fluctuations dominate. The gravity becomes as strong as other fundamental forces. This is the regime where quantum gravity effects are expected to be significant, potentially requiring a unified theory beyond the standard model. Spacetime may behave like a quantum form as proposed by John Wheeler, with virtual processes constantly fluctuating on extremely small scales. Early universe physics, the first is 10 up to the 43 seconds after the Big Bang, correspond to Planck scale conditions where conventional physics cannot describe the universe accurately. Implication for physics. The Planck scale sets a theoretical boundary for current physical theories. A breakdown of general relativity and quantum field theory at distances shorter than the Planck length or energies above the Planck energy. Classical and quantum descriptions fail. Challenge to relativity. Concepts like absolute length and time may emerge, raising questions about how special relativity applies at these scales. Hierarchical problem. The large difference between the Planck mass and particle masses like the proton highlights fundamental questions in particle physics. In summary, the Planck scale is a fundamental reference point in physics, making the limits where our current understanding of space-time and energy must be replaced by a theory of quantum gravity. It provides both a natural system of units and conceptual framework for exploring the earliest moments of the universe and unification of fundamental forces. And now I want to go through the Reissner Nordström metric. So here, these can not only pass the classical test of general relativity, but also serve as a potential alternative to dark matter and dark energy, with interesting implications in inflationary cosmology, gravitational waves, and particle phenomenology. It is worth exploring the impact of extra dimensions and higher curvature in black hole accretion. Various classes of black hole solutions have been derived which bear a non-trivial imprints of these ultraviolet corrections to general relativity. This in turn gets engraved in the continuum spectra emitted by the accretion disk around the black hole. Since the near horizon regime of supermassive black hole manifests the maximum curvature effects, we compare the theoretical estimates of disk luminosity with quasi-optical data to discern the effect of the modified background on the spectrum. In particular, we explore a certain class of black hole solutions bearing striking resemblance with the Bell and Reissner Nordström de Sitter, anti-de Sitter flat spacetime, which unlike general relativity can also accommodate a negative charge parameter. Now I want to talk about the Reissner Nordström metric. The Reissner Nordström metric extends the Schwarzschild metric to include the electrically charged non-rotating black holes. It introduces electric charge as a key factor impacting the space-time structure around a black hole. This metric predicts the different types of horizons based on the black hole's charge and mass. Understanding this helps in exploring how charged black holes interact with their surrounding and the practical potential gravitational and electromagnetic effects involved. Now I want to go through the practical examples. Black hole, the Reissner Nordström metric is a solution to Einstein's field equations in general relativity. It describes a black hole with the both electric charge and mass but no angular momentum. In the context of black holes, this matrix helps in understanding how charged black holes differ from non-charged ones, such as Schwarzschild black holes. It shows the presence of the electric charge influences the black hole's properties, including the size and structure of the event horizons. Understanding the Reissner Nordström metric fundamental of the charged spherical solution, the Reissner Nordström metric is a fundamental solution in the field of general relativity, providing crucial insight into the nature of charged spherical body in spacetime. This metric extends the Schwarzschild solution, which describes the gravitational field outside the non-rotating, uncharged, and spherically symmetric mass by incorporating electric charge as an additional parameter. The Reissner Nordström metric is not only significant for its theoretical implication, but also for its applications in understanding astronomical phenomena such as black holes. Key features for Reissner Nordström metric. As its core, the Reissner Nordström metric is characterized by two primary parameters, mass and charge q. These factors play a pivotal role in determining the spacetime geometry around a charged, non-rotating spherical object. The metric is expressed in natural units c is equal to g is equal to 1 as this equation. This equation reflects the deviation from the flat spacetime of spatial relativity introduced by the mass and charge of the central object. The presence of the electric charge adds the repulsive term q to divided by r2 to the gravitational potential, altering the spacetime curvature significantly. Compared to the Schwarzschild solution, horizon is a Reissner Nordström geometry. A notable aspect of the Reissner Nordström solution is the existence of horizons similar to those found in the black holes. However, the nature of these horizons differs due to the presence of charge. The solution predicts two distinct horizons: event horizon and quotient horizon. Event horizon located at r is equal to m plus square root m2 minus q2. It acts at the point of no return for matter and light. Quotient horizon situated at r is equal to m minus square root m2 minus q2. This inner horizon has intriguing theoretical implications for space-time structure and singularities. The existence and properties of these horizons are deeply influenced by the relationship between the mass and charge of the object. When the charge equals or exceeds the mass q is greater than m, the nature of the space-time charge drastically leading to a next singularity. This scenario challenged the cosmic censorship hypothesis and has been a subject of extensive data debate in theoretical physics. In the next sections, we will delve deeper into the physical implications and applications of the Reissner and Nordström metric, exploring its role in the modern astrophysics and theoretical physics. Physical implication and applications of Reissner Nordström metric. The Reissner Nordström metric is not just a theoretical construct. It has practical implications in understanding various astrophysical phenomena. One of the most intriguing applications is in the study of black holes. Specifically, the metric provides a framework for analyzing the property of charged black holes, which are theoretically possible or considered rare in the universe due to the natural tendency of astronomical objects to neutralize their charge. Another significant application in the realm of the quantum gravity and string theory, the unique properties of Reissner and Nordström black hole, particularly in the extremal case where the charge equals the mass, Q is equal to m, provide the fertile ground for testing theories of quantum gravity. This scenario results in the zero temperature black hole concept, crucial in the study of Hawking radiation and entropy of black holes. Challenge and controversies in the Reissner and Nordström solution. Despite its theoretical elegance, the Reissner and Nordström solution is not without its challenges and controversies. One major issue is the concept of net singularity, which occurs when the charge exceeds the mass q is greater than m. So the conclusion can be the Reissner Nordström metric stands for a cornerstone in the study of general relativity and astrophysics. It extends our understanding of space-time by incorporating the effects of the electric charge, offering a more comprehensive picture of gravitational field around the celestial bodies, while practical existence of such charged black holes in nature is debatable. The theoretical insights provided by this metric are invaluable. They not only deepen our understanding of black holes and cosmic structures, but also challenge and refine our theories in quantum mechanics and general relativity. In conclusion, the Reissner and Nordström exemplify the beauty and complexity of theoretical physics. It reminds us that our exploration of the universe is an ongoing journey filled with the mysteries and wonders waiting to be unraveled. As we continue to probe the depths of space, solutions like Reissner and Nordström metric will remain essential tools in our quest to understand the cosmos. The related concepts can be Kerr Newman metric, Schwarzschild metric, modern physics, Kerr metric, rotating black holes, Kerr metric, and also the Schwarzschild radius calculations. The Kerr metric for Newman, Kerr Newman metric. Kerr Newman metric is solution to Einstein fields equation in general relativity describing the spacetime structure around a charged rotating black hole. It generalized the Kerr metric by adding electric charge into the mix. This metric helps in understanding complex gravitational and electromagnetic fields interactions. The properties of black holes, such as their event horizons and ergospheres, are significantly influenced by their charge and spin due to this metric. Practical examples of black holes. The Kerr Newman metric is a solution to Einstein's field equations in general relativity that describes the spacetime structure around a charged rotating black hole. Unlike non-rotating uncharged black holes described by Schwarzschild metric, Kerr Newman black holes are charged and characterized by three parameters: mass, angular momentum, and electric charge. This metric helps in understanding how electrically charged black holes interact with the surroundings, including the bending of light and the behavior of matter near these exotic objects. Insights from the Kerr-Newman metric are crucial for astronomers and studying the dynamic processes in the vicinity of black holes in the universe. Understanding the Kerr-Newman understanding Kerr Newman metric, exploring charged rotating black holes in general relativity. The Kerr Newman metric represents a solution to Einstein equations of general relativity that describes the spacetime geometry in the vicinity of charged rotating black holes. This complex yet fascinating concept combines aspects of electromagnetism with the wrapping of spacetime, offering insights into some of the most extreme environments in the universe. The foundation of the Kerr Newman metric. The Kerr Newman metric extends the Kerr metric, which describes rotating but uncharged black holes. By incorporating electric charge, it is characterized by three parameters: mass, angular momentum, and electric charge. These parameters collectively shape the geometry and properties of the black hole and its surrounding spacetime. Geometry of spacetime around a Kerr Newman black hole. In the Kerr Newman metric, spacetime is distinctly wrapped due to the black hole's rotation and charge. The solution predicts the existence of an event horizon and an ergosphere. The event horizon is a boundary beyond which nothing and not even light can escape the black hole's gravitational pulls. The ergosphere, a unique feature of a rotating black hole, is an oblate a spheroid region outside the event horizon where the spacetime is dragged along by the black hole's rotation. This dragging of spacetime, known as a frame dragging, has the profound implications for the energy extractions and dynamic particle around the black holes, implications and astrophysics and physics. The study of Kerr-Newman metrics has significant implications in both astrophysics and the fundamental physics. It provides theoretical foundations for understanding the behavior of the matter and electromagnetic fields in the complex in the extreme environment near charged rotating black hole. Additionally, it offers a playground for testing the limits of general relativity and exploring the potential unification of gravity with other fundamental forces. For instance, the Kerr-Newman metric allows astrophysics to model the accretion processes and jet formation observed in active galactic nuclei and quasar. These phenomena involve complex interactions between the black hole's gravitational and electromagnetic forces and the surrounding matter. In the realm of theoretical physics, the Kerr-Newman solutions raises intriguing questions about the nature of singularities and the quantum aspects of the black hole. It challenges the physics to reconcile the classical theory of general relativity with the principles of quantum mechanics, paving the way for the development of the theory of quantum gravity. The exploration of the Kerr-Newman metric not only enriches our understanding of black holes but also pushes the boundaries of our knowledge in the fundamental physics, promising to unveil new mysteries of the cosmos. Exploring the quantum realm and thermodynamics of Kerr-Newman black holes. The Kerr-Newman matrix is not just a theoretical construct; it has practical implications in the study of the black hole, thermodynamics, and quantum mechanics. The properties of Kerr-Newman black holes, such as temperature and entropy, can be explored through the lens of the quantum field theory in Kerr spacetime. This approach has led to the groundbreaking insights, including the predictions of Hawking radiation, quantum mechanical phenomena where black holes emit radiation due to quantum effects near the event horizon. Challenge and controversies in Kerr Newman black holes studies. Despite its elegance, the Kerr Newman solution is not without the controversies and challenges. One significant issue is that the physical reality of such black holes in astrophysical scenario, it is rare to find black holes with significant charge, as they tend to neutralize quickly by attracting opposite charge from their surroundings. These aspects make the existence of Kerr Newman black holes in nature a high speculative. Additionally, the inner structure of Kerr Newman black holes, particularly the nature of the singularity, poses theoretical challenge, and unlike the simpler Schwarzschild black holes, the singularity in a Kerr Newman black hole is ring-shaped, leading to complex causal structures and the theoretical possibility of closed time-like curvatures, which could imply the time travel under certain conditions. The future of the Kerr-Newman metric research. Future research in the field of Kerr-Newman black holes is poised to explore deeper into the realms of the quantum gravity and high-energy astrophysics. With advancement in observational technologies like gravitational wave detector and the Event Horizon Telescope, there may soon be more empirical data to test the predictions of the Kerr-Newman metric and enhance our understanding of these enigmatic celestial objects. Moreover, the continuing development of quantum gravity theories such as string theory and loop quantum gravity may provide new insights into the microscopic structure of space-time around black holes and the fundamental nature of singularities. Now I want to go to the conclusions. The Kerr-Newman metric, a corner a cornerstone in the study of general relativity, continues to captivate physicists and astronomers alike. Its complex description of charged rotating black holes challenges our understanding of the universe and probes the limits of the modern physics with direct evidence for Kernium and black holes remain elusive. Their theoretical study provides invaluable insights into black hole dynamics, quantum field theory, and the quest for a unified theory of physics. As we delve further into the cosmos, the mysteries of the Kernium and black holes beckon, promising revelations about the very fabric of space-time and the ultimate nature of reality. Now I want to talk about the Schwarzschild metric. The Schwarzschild metric describes a gravitational field outside a spherical, non-rotating mass like a planet or star. It is a solution of Einstein's equations of general relativity, indicating how spacetime is carried by mass. This metric predicts phenomena such as gravitational time dilation and the bending of the light. The Schwarzschild metric provides a solution to Einstein field equations in general relativity, describing the spacetime geometry surrounding a spherical non-rotating mass such as the black hole. It reveals how space and time are wrapped by the intense gravity of black holes, indicating, for instance, how time slows down near them. This concept is crucial for understanding how black holes influence light and orbiting objects, shedding light on the extreme gravitational effects they exhibit. Understanding Schwarzschild's metric, a gateway to black holes and spacetime curvature. The concept of the black holes and the curvature of spacetime are fundamental elements in the realms of the astrophysics and general relativity. At the heart of the understanding these phenomena lies the Schwarzschild metric, a solution to Einstein's field equations that provides a mathematical descriptions of space-time around a non-rotating spherical symmetric body. This metric, named after Carl Schwarzschild, who first proposed it in 1916, has been instrumental in our understanding of black holes and the nature of gravity. Decoding the Schwarzschild metric. The Schwarzschild metric is expressed in a form that highlights the influence of mass on the surrounding spacetime. Each equation is given by these equations here. They represent the infinitesimal interval in spacetime. G is the gravitational constant. M is the mass of the spherical body. R is the radial coordinate distance from the center. C is the speed of the light, and T and theta and phi are the time and angular coordinates, respectively. This equation encapsulates the distortion of time and space due to the gravitational field of the massive object, the black holes, and the event horizon. The Schwarzschild metric has significant implications in the study of black holes. A critical concept derived from this metric is the event horizon, the boundary around the black hole beyond which no information can escape. The radius of this event horizon, known as the Schwarzschild radius (RS), is defined as Rs is equal to 2 gm divided by c2. This formula reveals that the event horizon size is directly proportional to the mass of the black hole. With the Schwarzschild radius, the escape velocity exceeds the speed of light, making it possible for light or any form of matter to escape the gravitational pull of the black hole. This unique characteristics of black hole predicted by the Schwarzschild metric has fascinated astronomers and physicists alike, leading to extensive research and discoveries in the field space-time curvature and gravitational lensing. Another profound implication of the Schwarzschild metric is the concept of space-time curvature. According to general relativity, massive objects cause a curvature in space-time which is felt as gravity. This curvature is what Schwarzschild metric mathematically describes. An observable consequence of this curvature is gravitational lensing, the bending of the light around massive objects, which has been observed in astronomical studies and serves as a key evidence for general relativity. Exploring the Schwarzschild singularity and time dilation. At the core of the Schwarzschild metric lies the Schwarzschild singularity, a point where the curvature of space-time becomes infinite. This theoretical singularity, located at the center of a black hole, represents a boundary where the laws of physics as we understand them cease to apply. While still a subject of intense theoretical research, the singularity highlights the complex and intriguing nature of black holes and the limits of our current understanding of the universe. Practical implications and observational evidence. These practical applications of the Schwarzschild metric extends beyond the theoretical physics. It has been crucial in the development of the technologies like global positioning systems (GPS), and where the understanding of time dilation due to the Earth's gravity as predicted by the metric is essential for accurate positioning. Additionally, the study of orbits around black holes, particularly for stars near the supermassive black hole at the center of our galaxy, provides observational evidence supporting the Schwarzschild metric and general relativity. Future prospects in the astrophysics and quantum gravity. The study of the Schwarzschild metric opens pathways for future research in astrophysics and a quest for a unified theory of quantum gravity. It remains a foundational tool in investigating phenomena like the possible existence of wormholes, the nature of space-time singularity, and the quest to harmonize general relativity with the quantum mechanics. As our observational technologies improve, we inch closer to testing the predictions of the Schwarzschild metric under extreme conditions, potentially revealing new secrets of the universe. Conclusions. The Schwarzschild metric stands as a cornerstone in our understanding of general relativity, black holes, and the curvature of space-time. Its introduction by Carl Schwarzschild and subsequent developments have profoundly influenced our comprehension of the universe, from the concept of the event horizon and black hole singularities to the practical applications in technical like GPS. Schwarzschild metric continues to be a vital vital tool in both theoretical and observational astrophysics. As we delve deeper into the mysteries of the cosmos, it will undoubtedly remain pivotal in unraveling the complexities of our universe and possibly in bridging the gap between the relativity and quantum mechanics. Modern physics, introduction to the modern physics. I hope that it helps you to understand some sort of conceptual. Today is the 14 days of July 2026. Time is 7 in the morning. Thank you so much for watching my tutorial video. And if there is any uh, simulation for this literature, you can find it from my github.com/masterscript or /Kashi script or /Safra script. So it seems that I have a little problem.